Respected viewers, in today's lecture, we will discuss the introduction to data communication and networking. Our objective is to have a look at the communication model with the suitable examples and illustration. Then we'll have a basics of data communication with proper illustration. We will then move on to the fundamental characteristics of data communication. Then we will have a look at the data representation, that is text, numbers, image, audio, and video, including very basics about uh, image compression and video compression. Then we will move on to the components of data communication, and finally we'll have a look at the data flow. That is, we will try to cover simplex, half, and full duplex communication. Now, when we talk about the communication model, we will actually have a source which will generate the data that has to be transmitted through a medium to a destination. Then we will have a transmitter which will actually convert those data into transmittable signals. We will have a transmission system which may have carriers which will carry the data to the destination. Then we will have a receiver unit which will convert the received signal into data, and we will finally have the destination which will be taking the incoming data. Now this is the very basic illustration of a communication model. It's a simplified communication model. On the left hand side, we can see in the general block diagram, we have a source and the transmitter. So those two are actually the source system. And on the right hand side, you can see it is the destination system, which is comprising of a receiver and a destination unit. Now, in between the left hand side and the right hand side, that is the source and the destination system, we have a transmission system which will actually carry the information from the source to the destination. Now, if we try to go for an example, we can just think about our workstation or our computers, which basically sends out information in the form of digital signal. Now, the digital signal, previously we used to had a public telephone network where we used to have telephones which were basically carrying analog signal. But since the information transmitted by the computer systems are digital in nature, we had to have a interface or a communication device which will actually take the digital information, put that on the analog carrier, and transmit through the underlying public telephone network. We usually call that modem. And that is modulator and a demodulator equipment. In short, we used to call that modem. And the modem used to put the data, that is the digital information, over an analog carrier and send it through the existing public telephone network. And on the other hand, again, on the destination side, or the transceiver side, uh, there was again a modem which used to get the digital information out of the analog carrier and send it to the destination system, which can be a server which can accept the information and again transmit back the answer to the sender. In our case, it's the workstation. So this is a very simplified communication model, and with an example we have seen in this diagram. Now let's move on to the data communication. Here, if we try to understand what the telecommunication means, here the communication which is done at a distance is usually called telecommunication. Now, the word data here actually means that there is a information, whatever be its form, it has to be agreed upon by both the parties, who are one is sending, another is receiving. So here the data basically refers to the information. Either it can be in text, it can be number, it can be image, audio, video, whatever it is, and the parties which are exchanging the information agree to it. Now, our data communication here also means the exchange of data between two devices via some form of digital medium, such as a wire, cable, wireless communication is also possible. And if we look into the simplified data communication diagram, on the left hand side, you can see the information, the input information in the form of a text. Here we are taking the example of a text from the source. It has been converted into digital bit streams. Then it is transmitted through an analog channel, and so the digital bit information is put on a carrier may be analog in nature, and then there is a transmission system, can be a guided, can be a unguided media, and then on the receiver end, that carrier is accepted. From there the data is extracted, and again the digital bit streams are formed and sent to the destination, where again it can find the information, that is the output information, to the destination system. Now let us have a look at the characteristics of a data communication system. The characteristics, basically, first of all, it's the delivery. The system must be capable of delivering the data to the correct destination. This is a very important thing. So if I am sending a piece of information to a particular destination, say X, then the data should not go to Y destination. It should actually go to the X destination. So the correct delivery is very important. Then the data must be received by the intended device, or the user that we were discussing. And the next part is the accuracy. Now, the system must deliver the data accurately. The data that have been altered in transmission and left uncorrected are completely unusable. So while sending a data to a particular destined destination, if the data gets altered during transmission, and when it gets altered and it is left uncorrected, so the information which was actually sent is not received by the destination system, and the information might have changed. So the accuracy is very, very important. So if I send ABCD to a destination system, that particular destination system must receive the thing as ABCD, not DCBA or something else. So accuracy of the system is very, very important. Now, timeliness. A system must deliver the data in a timely manner. If I am sending a data, I will expect that to reach the destination uh, in a certain period of time, which may include the transmission time, which may also have the delays due to congestion, traffic, whatever it is. But suppose I have sent the data today, and the destination has not received the data even after 3 days, then that is unacceptable. So whenever we send a data, it must be delivered in a timely manner. That in a timely manner should um, we also must consider the delays, transition, the congestions, delays due to congestion, traffic. So apart from that, it must send the data in a timely manner. And the data which are actually sent very late are actually useless. Okay, in case of video and audio, uh, whether we talk about video or audio, in a previous discussion, if we considered that as a text or some numbers or something were sent to a destination system, it was received little late, that is acceptable. But if sent after a long time, it's useless. But if we talk about video and audio, it is completely different. Here the time to delivery means delivering the data as they are produced, in the same order that they are produced, and without significant delay. So this type of delivery is actually termed as real time transmission. Now, another thing which we can discuss is the jitter. Here, the jitter refers to the variation of packet arrival time. It is the uneven delay in the delivery of audio or video packets. Example: suppose we have video packets which are sent every 30 milliseconds, and some packets arrived with a 30 milliseconds delay and others arrive at 40 milliseconds delay. Then you can see there will be an uneven quality in the video, which is the result of it. So when we send information, usually audio and video, the first of all, the pattern in which they are sent should be received in the same pattern, so that the meaning doesn't get altered. And since we are sending packets of data, it has to be received in order, and without much significant delay. If one packet is received in a particular delay and others with more delay, then the entire video gets jumbled up, and the quality of the video falls. So this is actually a jitter. Now let's have a look at the data representation part of it. Now the data can be text, can be numbers, images, audio, and video. So in data communication system, we basically send information in the form of digital bits and strings. So we have to somehow represent all these things in zeros and ones. So how are they represented? So if we talk about text, text is actually represented as a bit pattern, that is the sequence of zeros and ones. And we have different patterns designed to represent a text symbol, and we call this a code. Usually the coding system is called Unicode, and with the use of 32 bits, can represent symbols or character used in any language in the world. So there are other ways of representing, that is, we have the ASCII. Then we have uh, we also know that it uses 7 or 8-bit representation, where 8-bit representation of ASCII is called extended ASCII. Then if we take an example, the letter A in ASCII is represented as 65 in decimal, or 01000001 in binary. Now, there are other formats also. We have UTF-80. It's a variable length character encoding. Basically, it ranges characters from different languages, scripts, emojis can be done, and special symbols. Then we have UTF-16. It represents character from Unicode Basic Multilingual Plane (BMP) with a single 16-bit unit. Then we have UTF-32, we have base 64. These are methods to encode binary data into a safe and predictable ASCII format. Then we have hexadecimal encoding. Then we also have certain escape sequences. In context of escape sequences, text is represented using escape sequences with a combination of characters which are non-printable characters or special symbols. Examples is slash n represents a new line character, and slash t it represents the tab character. Then we have the numbers. Computers usually understand zeros and one. So if we represent that in 0 and 1, it's binary. We call it in short as bit. So each digit is called a bit, short for binary digit. Then we have a sequence of bits in a binary form. Then again, how are the integers represented? Now we can have unsigned integers. If we consider 8-bit, then those complete combinations of 8-bit can be used to represent a positive unsigned or a positive integer. The combination can go from 0 to 255. Then we can also represent negative numbers. To represent negative numbers, we usually follow 2's complement integer system, where the most significant bit is actually the negative weight, and others provide us the magnitude of it. Then we have floating point representation. Usually the floating point representation IEEE 754 format is usually considered, and it represents a wider range of values. And the standard defines how to represent real numbers in using a sign bit, exponent, and a fraction. Also, it represents a number with wide range of magnitudes and precision. We will have an example. You can see the example here, where we have a floating point format, which is IEEE 754 32-bit precision. Here you can see the most significant bit is the sign bit, which is 1 for negative, 0 for positive. Then we have the exponent part, the 8 bits. Then we have the mantis at 23-bit part. So also we can see an example where minus 248.75 has been represented using this format. So then we have the fixed point. In a fixed point representation, bits are allocated for the integer and the fractional part of a number. You can see this example where a fixed point number representation has been shown. And then we go on to hexadecimal system. Suppose hexadecimal systems or the hexadecimal digits correspond to 4 bits, and it makes easier to work with and visualize binary data. And it is often used in displaying binary values in a more compact and human readable format. So suppose there is 23, it's written decimal, and 0 to 9 in binary is same as hex. 10 is represented by A, 11B, 12C, 13D, 14E, and 15 as F. So you can see after 9 there are 6, which are 1, 2, 3, 4, 1, 2, 3, 4, 5, and 6. You can very easily see 10 is A1, 11 is B2, 12 is C3, 13 is D, 4, 14 is E, it's 5, and 15 is F, it's 6. So after 9 we have 6 more. We usually consider A, B, C, D, E, F for next 6 to represent in hexadecimal system. And to do that, you can very well understand this by just converting 23 directly to binary, where you can see we have the 8-bit representation where we have the weights written 1, 2, 4, 8, 16, 32, 64, and 128. To represent a decimal number system in 23 in binary, you need to first find out which under which I can put a 1. So here I can put a 1 at 16. If I put a 1 at 32, it goes beyond 23. So very next one is 16. So I'll put 1 there, and I will then see I have to add 7 more to get a 23. So I cannot put a 1 under 8. I will put other ones under 4, 2, and 1. So I get a binary representation of 23, and this then can be converted into hex, where we take the upper nibble, that is D7 to D4, represent that this is 1 actually, and the lower nibble, that is from D3 to D0, this is 7. So in hexadecimal system, 23 in decimal can be written as 17 in hexadecimal system. So if we have information in binary domain, so it's very easily readable form. Again, binary coded decimals, this is another way of representing in here. Each and every decimal is coded using binary. So here we can see that we have a decimal 3, 5, 6. 3 is considered separately, 5 is considered separately, 6 is considered separately. Code them using 4-bit binary. So here 3 is 0011, 5 is 0101, and 6 is 0110. So decimal to BCD is actually binary coded decimal. It is used when exact decimal representation is required, such as in financial systems. Now let's have a look at the representation where we have Graycode. This is another way of representing numbers. Now in Graycode, the binary number system where successive values differ only by 1 bit. So here we can see its application is in various applications like rotary encoders to prevent errors during transition. Now you can see we have only considered till 8. You can see the binary code till 8 and corresponding gray code. You can just see we have just said that the successive values differ only by 1 bit. So here you can see this, for 0 it is same, for 1 it is same, but for 2 you can see, since there was a change in the LSB, it will not change for the next one, but there will be a change in the next bit, which is 0 to 1. Similarly, for the next one, there was a change here, so this will remain the same, but this will change to 0. So this is how a Graycode differs from the binary code. Now the next one is the ASCII. You can see this as the numbers which are represented using corresponding ASCII or Unicode characters. Here you can see 48 represents 0, 49 1, 50 for 2, and so on. And you can also see the alphabets and special characters being encoded using ASCII. Now let's go to the next one. That is the image. Now image are portrayed using a very small component, or the tiny dots. otherwise known as pixel. So each of it possesses a distinct bit arrangement. Now the pixel is the smallest unit of information of any picture or any image. Now you can see the on the left hand side you have a image, and the box that you can consider is actually the area which we are considering. And uh, and if we zoom it, we can see each and every square box represents a pixel. So you can also see here, uh, we are trying to get the closest view of this area. So here we can see one square box, and if we magnify that also, we can see one square box. Now this is the smallest possible component of a picture. We usually call this a pixel. Now now when we take a photograph, or when we have a picture of or when we consider an image, the image, when is represented with many pixels, higher the pixel, the resolution is better. As you can see from this, when we have a 16 next to 16, the resolution is absolutely, we cannot even recognize what's there in the image. So when we increase the pixel size, that means the smallest units, the more we are compressing, the more we are putting pixels into the image, we can see that the image quality is getting better, the resolution is getting better. But the only problem with this is we need huge memory space to store the high quality images. So to boost the resolution of any image, we need to have higher pixel. Now you can see the representation of image. Here we have a black and white image. Now each pixel is assigned a bit pattern, and that signifies the level of brightness ranging from dark to light. So if we consider this area here, each and every pixel is assigned a value. Now this has been arranged in a matrix format. Now this actually ranges from a lower value to a higher value. Each value will represent the level of brightness of that particular pixel. Now, if we talk about the color images, now when we talk about true color, it is a 24 bit. So we all know there are primary colors are red, green, and blue. So if the pixel is each pixel is being assigned a specific bit sequence, in true color the representation of each pixel is represented in 24 bits. So we can see that blue has been given 8-bit green, 8-bit red, 8-bit. So depending on the combination of these three, the intensity of the blue, green, red, and the mixture of this will create different colors. And this represents the true color display. So in a particular color picture, the pixel actually here is a 24-bit, which is called true bit color, and it's the intensity of red, green, and blue, which actually gives out different colors of a particular pixel. Now let's see an example. This is an example of a image. This is a color image. So if we can see this one, this provides the intensity of this particular pixel in RGB format. Similarly, this one is having different value. You can see this pixel is also having a different value. So here it was comparatively darker, light, and little less light compared to this. So this is the lightest pixel, this is the darkest pixel, and this is between the darkest and the lightest. So you can see the values which are actually providing the information about the smallest component, the pixel, which is again having the different components R, G, and P. So let's move on to the next part, where we can see that any image which is there will have to be transmitted through a transmission medium. So before that, we need to actually compress the image. So this is a diagrammatic representation of image compression technique, where we have on the compression side we have transformers, where the image is taken as a matrix, and it is transformed into lossless transformation. Then we go for a quantizer, and usually quantizers are lossy, and it is encoded, then transmitted through the channel. And when it is received on the destination side, there we go for decoder, that is the opposite of encoding. And then dequantizers are used, and then the inverse transformation, and we again receive the image. But during this entire process, we have to remember, whenever we compress an image, some portion of it is lost, and when we again decompress, we will be able to see that some information has been lost. This is called lossy compression. Now let's move on to the next part, which is the audio. Now we have to remember that audio is very different from text, number, or images. Audio is an analog in nature. It's continuous with respect to time. So the systems which we use today are digital systems. We cannot directly talk to a digital system. So what we need to do is we have to first convert the sound waves, those are mechanical waves, into electrical using a microphone. And then we have the electrical output, that's an again analog in nature. Then we will have to go for digitization. Now digitization, the primary section of any digitizer here is the sample and hold circuit, which after that we have the quantizers. And the quantizers may follow certain techniques. It may be a pulse code modulation, it can be delta modulation, it can be adapted delta modulation. There are different methods that are used. Usually the most usually used technique is a PCM, that's called pulse code modulation. And using that we transform the mechanical wave, that is the analog audio wave, into digital, and then we can transmit that through the system to the destination system. And this can be seen pictorially shown here. On the left hand side we have the mechanical wave, the sound waves converted by microphone. Then we have converters which convert analog to digital conversion, where we have ADCs, AD converters. And then it's converted into digital, then it can be transmitted and again received by your destination system. Now let's move on to the video. Now video is actually we are referring to something which is recorded or broadcasting of a picture of a movie. Or video can be either produced as a continuous entity by a TV camera, or it can be combination of images, each a discrete entity arranged to convey the idea of motion. Now in today's data communication system, we have digital videos which are compressed and sent through the digital channels or the transmission channels. Now what is actually a video? When we talk about video, it is actually a collection of frames. It is actually collection of frames, that is pictures. When they are sent together, or when they are seen together in a particular rate, that is suppose we capture a motion, a video, or a video which is captured using different picture frames. When they are run together at 30 frames per second, then because of our eyes we will not be able to distinguish between the changes from one frame to another frame if it is above 26 frames per second. So if we have different picture frames run together at a rate of 30 frames per second, then it will give us a feeling of a video. So video clips are we can say that the video clips are made of a sequence of individual images or frames, hence video compression. uh, Algorithms share many concepts and techniques which are still image compression algorithms. So again, in this picture we can see that a person is throwing something. It has that particular thing has been captured using 6 frames. The information that was captured by the 6 frames is less compared to the information captured by this many frames. When we capture any motion with many frames, the details of the video is enhanced. But whenever we do that, again we are increasing the size of the memory required to store this particular information. Again, the problem associated with data communication is we need to send this motion pictures which are of huge size through our communication channel, which may not be able to handle the bitrate at which it should be sent in order to visualize the video properly. So again there is a need for compression. We usually go for MPEG, which is the motion pictures expert group, which is a method to compress video. And in principle, whenever we capture any motion, there are certain things in a frame which are which almost remains static even on the next frames. Only there are few things which change from the base frame to the next frame. So in order to compress those, well, there is a technique that has been used in MPEG, where we have in temporal compression, MPEG usually divides it into a set of 3 categories, which is called I frame, another is called P frame, and the other one is called B frame. So on the top of this diagram, you can see 1, 2, 3, 4, 5, 6, 7. So this is compressed, where we have I, B, B, P, B, B, I is the format in which it has been sent. So you can see the I frames is the intra-crowded frame, is a independent frame that is not related to any other frame. It is the independent frame which actually has the most information in it, and uh, not the frame sent before or after. Okay, so they are present at a regular interval. So you can see in this diagram, if this is I, this is another I, it is present in a regular interval. So P is a predicted frame is related to the preceding I or P frame. In other words, each frame contains only the change from the preceding frame. So what I was talking about is the P frame will only have the change from the previous frame. So there is a base frame, and the next frame that has been captured. In the base frame and the next frame only there will be few changes, only those things are kept. Okay, so next is the B frame. It is the bidirectional frame, is related to the preceding and the following I frame, that is or P frame. So it can have a preceding I frame, following P frame, or preceding P frame or following I frame. So It is a bidirectional frame, and we have to remember one thing: B frame is not followed by any other B frames. Okay, so in other words, B frame is relative to the past and the future. So these are the three frames that those were used for MPEG compression. We can have a detailed discussion about MPEG in our later lectures. Now let's move on to the components of data communication. And the components are message. You have a message that has to be sent. Then you need a sender, a receiver, a transmission medium, and a protocol. Now let's have a look at it. Now the message, here in this diagram we can see we have a sender, we have a receiver. Those two are connected via a medium. Now this medium can be unguided, it can be guided. Now when we talk about the message, it is the information data that needs to be communicated between the two, the sender and the receiver. Okay, the we have already seen the different types of data that can be sent. It's the text, numbers, pictures, audio, and video. Now we have a sender. Now the sender is the device which will be sending out the data, and it can be a computer, it can be a workstation, telephone handset, it can be a video camera, and maybe and so on. So here the sender is sending the information through the channel to the receiver. Then we have a receiver, obviously the sender, which is sending the information to the destined destination system, and the destination system should agree upon what the sender is sending, and then it accepts the information. Now we have the transmission medium. This transmission medium is actually the physical path between the receiver and the sender, and it can be guided. That is, when we talk about guided, it includes physical cables. Physical cables can again be categorized under different types, like twisted pairs, unshielded twisted pairs. Then we have coaxial cables, and then we can talk about optical fibers also, where the information is sent in the form of light. Then we can have unguided medium. That means somehow the sender and receivers are connected through wireless medium. It can be anything, it can be radio waves. There can be different communicating devices which sends out electrical waves and can be received by the receiver. And next is the very important thing, which is the protocol. That is, we all know that protocol is a set of agreed rules which actually governs the data communication between the two communicating parties. Now, without a valid set of protocols, it will be useless to send information from one side to the other side. It will just like a French. Suppose a sender is a French and receiver is a Japanese person. So when the French is talking to the Japanese person, the French is not able to speak anything else rather than a French. And the Japanese, the other person which is there on the other side, the person can only communicate, understand, and speak in Japanese. So even the French is sending some information to the Japanese, that other person will not be able to understand, because the set of protocols that they understand are separate. So a French, when talking to a French, then the two parties can understand, because they have a set of rules that their language, the language which they understand, so they can exchange information. So obviously here the protocol plays a very important role in having a successful communication between sender and receiver. Now let's move on to the data flow part of it. We'll be considering three. We have the simplex, we have the half duplex, and then we have full duplex. Now let's see what a simplex is. It is the simplest form of communication, and it is unidirectional in nature. That means it will be traveling from one side to the another side. Now we can have a example here. Here on the in the diagram, you can see on the left hand side we have a mainframe, and on the right hand side we have a monitor. Now usually monitor is a output device. It is a simple monitor. So the information which is sent out from the mainframe to the output device, and the output device is displaying the information. So there is no way that the monitor is going to send back anything to the mainframe. The only information that will come to the monitor is from the mainframe. So this can be termed as a simplex data flow. Now again, there are other examples, like we have keyboards. Those are considered as input device. Here the keyboard provides the information into the computer system. Nothing comes out from the computer to the keyboard. Actually, the keyboard, whatever we press in the keyboard, the information gets inside the computer, and the monitor only can accept the output. So all these are examples of simplex data flow. Now let's try to understand the utilization. In this case, the entire channel capacity is to send the data in one direction. So the entire channel is just used to send data in one direction only. Now let's have a look at the half duplex. Now when we talk about half duplex, we have two systems. Both the systems are trans receivers. That means it is capable of transmitting data as well as receiving data. So on the left hand side we have a trans receiver, on the right hand side we have a trans receiver. It can receive information, it can transmit information, but the communication channel that has been built between the two are is not suitable for two-way communication. You can just think about a situation of a road from point A to point B. The road can be accessed only by a car at a time. So if a car is moving from point A to B, then the cars waiting at B have to wait there till the other car crosses from A to B. So when it has crossed the point B, the other cars which were waiting at B can now travel towards A. So the channel between, or the path that is existing between the two trans receivers, can only be used once by anyone. It is another example of this is a walkie-talkie. When we talk about the walkie-talkie, the two persons are having walkie-talkie, having on a with a separated by a distance. When they have to send information to the other person, the person A will hold the channel and send his information, and the other person will then be receiving it. And when the person A has already completed sending its information, will release the channel, and the other person who is on the other side can then take over the channel and send the entire information. In this case, the channel capacity is utilized completely, and we can say that this particular channel doesn't require two-way communication. Now let's move on to the full duplex mode. In the full duplex mode, the both the station can transmit and receive information simultaneously. You can just think about a two-way street, where one of the street is used for vehicles to travel from A to B, and the other portion of the street is used for cars traveling from B to A. So the entire channel divided into two. One of the channels for upstream, another channel for downstream. None of the channel is interfering with the other channels. So here the traffic can be on both the directions. The example of this is a simple telephone, and the telephone, when we used a telephone network, we were able to hear as well as able to talk simultaneously, though human beings, when talking, usually can't compute other person talking to you. So maybe this is the human nature, but in a telephone network we can talk simultaneously when the other person is talking to you. So that is the example of a full duplex communication. So again, the capacity of the channel, however, has been divided between the two direction, but in both the directions it is to its capacity, is used to its capacity. So to conclude this session, we can say that we had a very brief discussion about the communication model with proper illustration. Then we had basics of the data communication with proper illustration. Then we had an idea about the fundamental characteristics of data communication, which included timeliness, accuracy, jitter, and reliability. Then we had a basic idea about the representation of data, that is the text, number, image, audio, and video, and very basics of audio, sorry, image and video compression. Then we had a discussion about the components of data communication, which included message sender, receiver, protocol, and the transmission medium. Then we had a very brief discussion about, with examples and illustration, about the simplex data flow, half and full duplex data flow. So I hope this was a introductory lecture on data communication. So I hope the lecture was informative and bit interesting. Thank you very much for having me and uh, listening to my video and watching my video for this lecture on data communication, introduction to data communication. Thank you very much.